Hello everyone, my name is Anvita Bansal and we are back with another lecture based on stacks and queues. So the problem that we are going to discuss today is maximum of all subarrays of size k. So let me just quickly check if you guys are able to see my screen. I think we are live. Okay, so I'll show you the problem statement. So this is the last question from our topic of stack and queue, and tomorrow we'll be starting off with linked list. So let's see what this question says. Okay, so this question asks you to return an array which contains maximum of all sub-arrays of size k. So basically, you are given an array and you are given a k which defines the size of the sub-array. So for each sub-array of size 3, for example, this is your sub-array. What is the maximum element from this subarray? 3. Then what will be the next subarray of size 3? It will be this. The maximum from this subarray will be 3. So that's how you are returning it. So the next subarray of size 3 will be this, and the maximum of this subarray will be 4. Same goes for all the subarrays of size 3. So the maximum from this subarray will be 5. The maximum from this subarray will be 5. That's what you are returning. The maximum from this subarray will be 5. That's what you're returning here. And the last subarray, the maximum of this is 6, which you're returning right here. So basically you have to return an array list which is containing the maximum from all subarrays of size k. Right? I hope the question is clear to you. Now see, this question can be solved in different ways. The brute force approach that might come to you, not even might, the direct approach that comes to our mind when we see of this question is that we traverse over the entire array for size 3, right? Let me just take this example so that I can tell you. The thing that I just discussed is actually the brute force approach itself. What it is that we are traversing over this entire array in size of 3. So it can be like your I, right? I starts from I is equal to 0. Let's say my I starts from here. My j will be, let's say, at this position. That will be I plus k, that is 3 minus 1. 0, 1, 2 at this index, right? This is where my j would be. For example, this is my window, okay? Now I will see what is the maximum. Let's keep iterating ARR of, let's keep changing my, maybe you can say, let's keep changing our j. I start from I equal to 0 and start from j equal to 0. The maximum is 1. Now you increment the count of j, index will come at 1. Maximum of these is 2. Let's store maximum here. It's 2. Now your j becomes 2. Next index, the maximum from there becomes 3. Now when you check your j minus I plus 1, that is, you want to know the size of the window, it is equal to k. So the maximum, the first maximum that you got is 3. You will store in some another array list 3. Now how are you going to handle? So you have to basically use sliding window technique. Very simple one, the brute force approach. Sliding window technique, in which you are now, you will be incrementing the count of your I. Now your I will be here, okay? Your I will be here. Again, start off with the same thing. You just calculated the maximum from this subarray. Now you have to calculate the maximum from this subarray. Got it? So again, you will be iterating over this. So this typically is n times k of time complexity, right? We don't want, actually we can optimize this time complexity. I'm not going beyond this because this is a simple one, and I'm assuming that you all can do this thing. This is basic iteration over this using sliding window technique. Once I came here, now I will increment the size of my I, and every time my j starts from I and goes till I plus what is your k minus 1th index. The maximum of j is this, right? And it starts off with I, and then you do j plus plus each time. And for each chunk of this window, you are storing your maximum in this another array list. So maximum from here will come here. Now your I is incremented. Bigger for loop is where my I is incrementing. I comes here. My j again starts from I, from this position, and so on and so forth, right? So this is one way. The thing is, how much time will it take? One entire traversal over this array, And for each traversal, you are actually traversing it 3 times. Every time you're traversing it, each element basically, except the first 2 elements, are typically we are iterating over that element almost k times, right? So this comes out to be n times k of time complexity. How do we optimize it? The second approach that we can use is by using max heap. Now what do you do in this max heap? Very simple one. If you know what heaps are, how we use a max heap, we can implement, we don't need to implement, we can use a priority queue of max heap type QUEUE, right? So this priority queue, I'm going to use it of type max heap, where I am going to store maximum of 3 elements in my heap, such that the maximum of those 3 elements is always found at the top of your heap. This is how your heap is going to look like. Since I am going to go ahead with a max heap, in every iteration, for example, I am iterating over this array, right? While your queue, you have initialized this priority queue, you have declared a priority queue of type max heap, right? Then you go over this array. For each element you store in your heap, you will check when the size becomes equal to 3, you will remove the priority, you will do pq dot, you will check what is pq dot peak, and then you will remove it. Okay, so pq dot remove, store that pq dot remove in an array list, right? Now when you go ahead with another element, suppose initially it was 1 2 3, so 3 2 1 is how your heap is going to look like. Now 3 will be removed from the top of your queue, it will be stored in an array list. Now the next element when I add is 2 3 1, so 1 2 3 2 3 1. For this case also, okay, yeah, so in this case you're not going to, when you see that from 1, when I'm adding 1 2 3, what is the max? That is 3. Now you take one more element, right? You take one more element and add to it, so the maximum for it also will be 3. You take that from the top of your queue. Now you add one more element, that is 4. So queue will adjust itself in such a way that the maximum of the elements that you are inserting will be found at the top of your priority queue. So this typically takes around height of this heap times of time complexity, and height is log n, right? Whatever the maximum height it can take will be of log n. So log k, n times log k can be the time complexity if we go ahead with heap, right? Now coming on to, so this is also a good approach, and you can use this. Actually this question can be solved using the sliding window itself, but the motive is to help you understand how can we solve this question using queue. Okay, and before I move on that approach, it's not very intuitive to think of a queue. It is intuitive if you are well aware of, or you have solved number of problems using queue, that in that case it can be, but otherwise it's not very intuitive. That's why we do not much try to solve that problem using DQ. But yeah, one thing is that approach is going to be maximum optimized approach for this particular question. Why? Now let's see. So we are not actually going to use a queue, we are going to use a better version of queue, that is a DQ. What do you understand by DQ? QUEUE. So DQ is actually 2 ways queue. That means in an ordinary queue, it follows first in, first out, right? Whatever element I insert, A, B, C, if I insert, so A will be removed. But the DQ's property is that a method is involved with DQ that is able to actually remove and insert elements towards the, insertion happens towards the end, but we can remove the end element also, and obviously we can access the front element. That is the property of queue. But in DQ what we get extra is that we can remove the last element from your queue as well. This is the property that comes with DQ. An extra property is that you can access and remove the last inserted element, which normally in queue we can't. You remember this, the last inserted element. Okay, fine. So making use of this, how are we going to solve this problem? So let me take this example 1, 2, 3. Let me write it. So we have 1, 2, 3, 1, 4, 5, 2, 3, 6. 1, 4, 5, 2, 3, and 6. This is your given array, right? This is your given array. 1, 2, 3, 1, 4, 5, 1, 2, 3, 1, 4, 5, 2, 3, 6. Okay. So how are we going to solve this question using a DQ? It's just that whenever we are using a DQ, right? First of all, let's say I have some indexes. My I, this is my I, this is my j. Currently my I is also at 0 and my j is also at 0. Let me write the indexes here. So this is index 0, index 1, index 2, 3, 4, 5, 6, 7, 8. So the basic idea behind this approach is that, see, I am going to maintain a queue in such a way that for every k size subarray, it is going to store only the elements which do not have smaller elements before it. What does this mean? You won't be able to understand it like this because it's not also explainable if I try to say it like this. What do we want to do is that we are going to maintain a DQ in such a way that for every k size window, right? For every k size window, I have that element in the front. I should be having an element in the front in such a way that there are no smaller elements before it in my array. How are we going to ensure this? So just have a look. So this is your first element. I insert it in my queue, right? Right now, let's say I is here, j is here. Now since I am going to iterate over this entire array using j. Now when I inserted this first element, let's move my j at this index. So the difference between I and j is going to tell me the size of the subarray that I am evaluating. So right now when my k given is 3, I can see that the size can be evaluated using j minus I plus 1. So j is 1, I is 0, 1 minus 0, 1 plus 1, that is 2. So 2, right now this ensures that I am within the window size. Now when I am inserting in the queue, I have to make sure that I only have elements which do not have any smaller elements before it. So I will ask, so my queue already has 1. My current element is ARR of j. Every time I am moving j, I am asking if the element that I am at currently, does it have any smaller element in the queue? Queue will say if it does have, I will remove that element from my queue. Why am I doing so? You will understand this thing. So first, because I want to insert 2, I want to make sure there are no smaller elements than 2 and I am within my window size so that I can have the maximum by the end of this k size iteration. So I found 1 is there, so I will remove 1 from my queue. Now I will add 2. Since I have added this 2, I will increment the count of my j. Fine, I will increment the count of my j. Now my j is here, right? Now next thing is what? Again you check the same thing. 3 you want to insert, but you found that 3 has a smaller element in your queue. So I will remove this element and I will add my 3 here. Now you see that when your j was here, j minus I plus 1, basically 2 minus plus 1, that becomes equal to window size. When it becomes to your equal, I inserted this element, I made sure of these things. Now what I want to ensure is that when I add, okay, you're adding the element and you are removing if you found a smaller element. Simultaneously, this is your answer array, which when you exceed the size of your window, for example j minus I plus 1, when it becomes equal to, your size becomes equal to k, that is the size of a window. That means now you have to declare the maximum of that subarray. So I will handle it using some else part. In my if part, what I am doing, while I am within the size of my window, I am ensuring that there are no smaller elements. If there are present, I will remove from my queue and I will keep adding ARR of j. Now when my size becomes equal to k or greater than that, then I have to take some step. That is, first of all, if I again, while I am trying to insert it, I will ensure there are no smaller elements. If there are present, I will remove it. This is my first thing. The same thing will go for if part also. The same thing will go for else part also. But there are some additional things that I'm trying to do. Since this is the end of my subarray of size k, this first subarray, this is the maximum size I can evaluate. That means this is the window of size k. That is why I am in else part. And I have ensured that there are no smaller elements. I inserted this element. Now, I have been doing this in such a way that I always get the maximum of window of size k in the front of my queue. So pq dot remove first, okay, or pq dot don't remove right now, pq dot peak, okay, pq dot peak. Even if you write peak or you write peak first, you can do anything. So that should be going to your answer array. So the first maximum you got is 3, which I will insert here. Now what I want to do, I also want to ensure if this peak element is equal to the element that is present at ith index, right? Which means that is the start of a new window of size 3. So I will also simultaneously remove it, which is not the case here, so don't worry. Let's do one dry run, then you will clearly understand. I'm going to add now. Okay, right? So this is the thing. Now, since you are done with this window, increment the count of I. So I is incremented once you have done your process for k size elements. Now you see that you are in the else part. Okay, whenever you are in else part, you must be at the position where your window size is k or greater than k. Fine. So you move your I as well as your j. So I was earlier at this window. Now my window is this. This is what I and j represent, start and the end of my window, right? Now you do the same thing. See, now when your j is here, again j minus I plus 1, that is equal to k. So I will go to the else part. In my else part, I am ensuring while my queue is not empty, okay, and also the last element that I have in my queue, since this is a D queue, I can access the last elements of my queue, and q dot last element, that is peak last, this is the method function you can use, that is smaller than your current element, ARR of j. That is when you have to remove from the front. That is when you have to remove the elements from the back, right? So you're going to do q dot or dq, write it dq dot, 1 second, let me write it, remove last. Okay, that's what you're going to do if you come in this condition. Then the next thing is, first let's check. Now the next element that you are at is 1. Does this condition hold true? ARR of j is greater than this element? No, it is not. So I will simply add 1. So you come out of this while loop, you simply add dq dot add last. In the last, we are adding this ARR of j, right? ARR of j is being added here, right? Then what? Okay, so I am at 1. I have added this ARR of last, and I increment the count of j and increment the count of my I. Fine. And also there is one more condition that I am ensuring, that the element in the front. Also one more thing that we missed here. Once we have added, in my answer I have to add the dq dot peak first. That is this element, because now it is telling me, since I am in the else part, that means the window size is either equal to k or greater than. It should not be, it will never be greater than k. We are handling it in such a way that at max the size can be equal to k only. So you have to also, now the element that is in the front of your queue will be the maximum for this window as well. So this window has maximum 3, so this 3 will be added here. Okay, this 3 has been added here. Move your I is here, move your j. Now your window size is from 3 to 4. Do the same thing. Your 4 you are trying to add, you are in the else part of your loop. So when you try to add 4, you will remove elements that are smaller than 4. You remove all the elements basically. Now you're adding 4. Okay, fine. Now what? You removed all the elements, then you added 4. In your answer, what is the peak element that you have? So the peak element that you have is 4, so you add 4 to your answer. You check that the element that is present in the peak first is not equal to I, so you don't have to worry about the window size. That means it is maximum k only, it's not exceeding k. Now you do I plus plus, I is here, j is here. The next element that you are going to add is error of j, 5. So I will check in my queue any smaller elements. Yes, I have, so I will keep removing it. Now I added my 5. When I added my 5, I have to add it to my answer because the peak first is 5 only. There is only one element, so 5 has been added here. Do the same thing. I comes here, j comes here. Now you are going to add 2. So 2 does not have smaller elements. I will directly add 2. Now in your answer, what is the peak? It is 5. So this represents that 5 is the maximum for window of size, window which starts at I and ends at j. So if you check 4, 5, 2, the maximum is 5. This is what is storing here. You got it? Now do the same thing. Now what? Now you move your I here, j here. 3, and for this window you will know that 5 is the maximum. So first of all, I'm trying to add 3. So for that I will remove the smaller elements. So now I have only 5 and 3. Fine. Now what? Now you check that what is the peak element, that is equal to 5. So the maximum for this window will also be 5. Now the next thing that I have been telling you, that we are ensuring that the peak element, if that is equal to ith element itself, that means that is the start of my window. And when I am going to do j plus plus and I plus plus. So in that case, if I try to add 6 and along with 5 being in the queue, that will exceed the size of my window, and I have to ensure that my queue only has elements at most of size k, right? Subarray. So I will be removing this element so that it does not create an issue when I try to add another element, right? Because if I do not remove it, for example, this was not 6, for example, it was 4, you will be adding 4 by removing 3, okay, and you will still have 5. So you will be returning 5 for this subarray. For this subarray, the answer that you will be returning will be 5, which is not right. This is the reason we are checking that the element in the front of my queue, if that is equal to I, that means you should be removing that, because now the next element which I will be adding, that will exceed the size of the k subarray. So the window should be limited to I starting and j ending, and j minus I plus 1 maximum should be equal to k. So I remove this element. Now I have 3 in my queue. Now I'm going to add 6. So for 6, I will remove this element from my array, from my queue, and I will add 6. Now there are no more elements to add. The answer for this window will be 6. So this is the answer that you are going to return for your question, this test case. Let's verify. 3, 3, 4, 5, 5, 6. 3, 3, 4, 5, 5. 6, right? I hope you understood the explanation. Let me just check if you guys have any doubts. Okay, so I don't see any doubts so far. So that's all that we are going to do for this question. Again, okay, so this thing, you can see that we are doing this entire thing in one pass. We are using a loop, for loop, where j starts from 0. I and j both are there, both are at 0, but the loop goes for j, right? For each element, we are using, for one iteration, we are just having two conditions, if and else, and we are taking our decisions accordingly. So at most, this approach is giving you time complexity of n, big O of n, and obviously some space complexity, which is big O of k, space complexity, because at max the queue is supposed to, we are creating a queue in such a way, that is the reason we have taken a D queue, in such a way that at max it will have only k elements, maximum of k elements at a time. It cannot exceed k. Fine. So I hope this question is clear to you. Let's move to the code and try to solve this question now. Okay, fine. So I'm just taking okay, then let's start off. check if my screen is cool. Okay, the first thing that I will have to take two space. One is the array list, which will be storing the answer that I have to return, and other one is the DQ, in which I will be storing the elements that I want to process. Fine. So let's take a DQ. You can directly use this DQ of type integer. Just a moment. Integer DQ equal, it's going to be of type new. You can take it array of DQ, new array, or of type linked list. Anything is fine. DQ, fine. Okay. DEQ U, DEQ U, E, DEQ U, E. Fine. Moving on, an array list of type integer, arr new array list. Fine. That is going to be right. Now let's make our int I equal to 0, j equal to 0. Now int, at any point in time we are calculating length, that will be equal to j minus I plus 1. But wait, before I have to take a loop while j is less than n, where n is the size of your entire array. Fine. Now, okay, now this is the length that I am evaluating. If this length is less than k, if this length is less than k, then what? Then you are adding your element, ensuring that any smaller element in Q is being removed. That's all that you are doing. Why? So for that, while your DQ is not empty, is empty, right? And this DQ dot last element, that will be DQ dot peak last. Okay, this element is smaller than your current element. ARR of j is your current element. If that is greater than, okay, if that is greater than this DQ dot peak last, in that case what you are doing, you are simply removing DQ dot remove last. Okay, once you are out of, if this, whether you go in this while loop or you don't, you are also adding that current element into your queue. So DQ dot, and in the last DQ dot add last this ARR of j. Fine. Okay, and then you do j plus plus. Cool. This is your if condition. In the else part, what you are going to do, you are going to do the same thing. First of all you're going to do the same thing. Okay, now the further things that we are going to do is, again, you are also adding DQ dot add last ARR of j. This will also remain same. Next thing is the answer, the ARR array that you have created, it should be answer because ARR is already given as argument. So ns dot add, this is an array list. In answer you are adding DQ dot peak first. Okay, this is the element that you are adding into your answer array. Then you are ensuring if DQ dot peak first, okay, peak first, that is equal to ARR of I. That means that is the end of your array. That means that is the I and j are at the extremes of a subarray of size k. So next, for adding next element, you will have to remove this peak element from your queue. If that is the case, then DQ dot remove first. Okay, DQ dot remove first. That's what you're going to do. And then the same thing as we did earlier, just that I will be incremented even if this condition is true, or even if it is not, you're going to do I plus plus and j plus plus as we did above. And then finally, this is your else part, this is your for loop, you return your ANSR. Okay, let's check if there is any. dq dot is empty is, what is the issue? Peak last. D if length is less than k, while dq is not, dq is empty, that is fine. ARR of j is greater than dq dot peak last. This is the problem. Now in 71 also same thing, because we copy pasted it. Let's check. I think again there is issue. Fine, let's try to submit it for all test cases. And we are done with this question. Okay, so that is all about this question. Hope you understood this. If you have any doubts, you can ask me. So you can clearly see we are doing this in exactly one pass. So the most optimized of the approaches that I discussed is using this DQ. Fine, so I'm just checking if you guys have any doubts. Hello Shihab Khan, I hope you understood the question. If there are any doubts, you can let me know. So I think that's all for today then, everyone. If there are no doubts, we will wrap it up. Try it yourself, the question. You can try to first do it with the brute force approach. Then if you want, you can try the heap approach. That is also a good one to understand heap. And then you can try with this approach. Okay. So let's wrap it up, everyone. See you all in the next lecture. Bye bye and take care.